last time we we looked at the anti-self-dual Yang-Mills equation. So remember, the context was that we, so geez, what else? Compact Lie group. We pick up principal G bundle over a 4-manifold, and then X is supposed to be oriented, connected, and we pick a Riemannian metric. And then if we take, that's a connection in P, that's its curvature. Its curvature is a section of the bundle of two forms. Tensor the adjoint bundle of P, and because we picked this Riemannian metric, the Hodge star decomposes the two forms into an orthogonal direct sum of the self-dual and anti-self-dual forms. And then what we want to look at, we decompose the curvature using that direct sum decomposition, and then we want to look at, well, our goal is to study the moduli space M of X and P depending on G, which is the set of connections that solve the anti-self-dual Yang-Mills equations modulo the automorphisms of the bundle. Okay, and since I see, there was a change of algebraic geometer. Last time there was Kolar, now there's Chen Yang. But just for the algebraic geometer, this, in the case that this is a Kähler manifold, then it's a famous theorem of Donaldson, Uhlenbeck, and Yau that we can identify this with a moduli space of semi-stable holomorphic bundles, principal GC bundles on X. But we want to study this from the point of view of differential topology, and one of the advantage of the differential topological point of view on moduli problems is they tend to live naturally. For an algebraic geometry, you tend to patch together moduli spaces from local variations. But in differential geometry, we often have the advantage that it sits inside a bigger space. And that space that it sits inside, so we're going to understand M sitting inside A of P mod G of P. A of P is all maybe C infinity connections. We'll specify that a little more carefully in a minute. In P, which is an affine space for the one forms on X with values in the adjoint bundle of P. Here, GP, that's the automorphisms of the principal bundle. But I'll now denote it GP. That's the set of, well, on the one hand, that's the set of maps covering the identity, which commute with the G action. But you can identify this in a natural way with sections over X of the capital add P bundle. That's the bundle where you take P times G and you take the quotient of this where, well, it's just, that's the right action here, but here it's the adjoint action. So, the principal bundle is not a bundle of groups, but this is a bundle of groups, the adjoint bundle. And just to be a little more concrete about that, if G is something nice like UN, then it's natural to look at the associated vector bundle Привет. Then, what do I want to say? Yeah. Then add P sits inside the endomorphism bundle of P. This is the unitary endomorphisms. Okay, so that I mean, it's good to have the general language, but in a specific case, this is a rather more concrete object. And here you see that it is a bundle of groups. On the other hand, if you want to recover P from E, then it's the bundle of frames, and it just has an action. It's not a bundle of groups. Okay. What else do I say? Yeah. Now. Right. So our moduli space then M of X of G, that sits inside the space of connections in P mod the space of gauge transformations. And so we want to understand this first. So we want to understand, and we'll sometimes call this BP. So BP you might call is the moduli space just of connections in P. And now we have to think about what kind of a space this is. What, is it, if the story is very different if G weren't a compact Lie group, this would be a rather horrifying topological space. It wouldn't be Hausdorff. But when G is a compact Lie group, it is a Hausdorff space. And in fact, it's kind of an infinite dimensional orbifold. So we want to address that. So we want to understand kind of, let's say, local structure of BP, understand its algebraic topology, and some friends of it. And then if we understand these things well enough, then, we're going to try to exploit the fact that this, this will be, with big quotes, a finite dimensional submanifold. Not true, but anyway, for first pass, think about that. I mean, sometimes it is, and if it were compact, then we could hope that it defines a cycle in here, and if we understand the algebraic topology, we can use that algebraic topology to define invariants eventually of the smooth four manifold. That's how it eventually goes, right? But So any questions about that much? No. You're going to suffer, I think. No? Yeah, you.
I will ask my questions later.
Okay. No. Okay. So. Okay. So that's kind of the goal, and then use a fundamental class of M to define invariants. And then we want to make some tools for computing them as well. Okay? So, well, first thing we should understand is, how nice is the action of the gauge group on the space of connections. So that the first thing to address is what's you should understand stabilizers of connections. Right, whenever you have I mean, as we'll see in a bit, that we can really think of this as this will give the structure of an appropriate topology, infinite dimensional Hilbert-Man, then fold. This will be an infinite dimensional Hilbert-Lie group. But in any case, whenever you're studying the quotient of a manifold by a group action, the thing that's your biggest enemy is when the stabilizer jumps. Stabilizers are sort of constant, then the quotient's a nice space. If it's not, then it jumps, and we need to do some harder work. So we need to understand what is the stabilizer of a connection A. So, well, by definition, it's gauge transformations that, and that preserve the connection. Now, what is a connection?
What's a connection?
What is a connection? Ashvath, give me a definition of a connection.
It's a differential operator on sections of a bundle.
With what properties?
With the appropriate properties.
ChatGPT answer, good. Szabo.
I could see kind of that.
Okay, so the one definition is, so. Thank you. Now that's a good definition. Good. So there's a notion of parallelism, right? If I've got my principal bundle, then if I have a path in the base, it gives me a way of, if I have a lift of the base point, I can lift the path in a unique way that's G equivariant. Right? So the group is acting here. And that data is determined by a splitting of the tangent bundle at every point of the total space into a horizontal subbundle that projects isomorphically onto the base. And then there's a vertical subbundle which is identified with the Lie algebra, but in a twisted way. I mean, the fiber you can identify with the Lie algebra, but the fiber at a point up here, because the Lie algebra is left invariant vector fields, and this is a right action, is related by the adjoint action. So it's a equivariant horizontal subbundle. And it's also a differential operator that maps, so the covariant derivative, let's say covariant derivative, which maps sections of the Lie algebra bundle to one forms with values in the Lie algebra.
But that's what it really is.
Well, no. It's really all three of those things. You know, and you will suffer if you don't see all three of them.
What's an LP equivariant horizontal subbundle?
What do you mean, what's an LP equivariant? It's a subbundle whose, so that,
Who's associated nabla operator?
no, it's a subbundle so that, I mean, it makes sense for a subbundle to be an LP subbundle. Hajvath, right?
How?
Later, buddy. Okay, so and we'll get to that.
So you said you're willing to give more lectures if you can.
Yeah, we'll get to that. Okay, but that's what it is. And now with this definition, I mean, with these two definitions, this makes sense. This is an automorphism of the total space, and it's supposed to preserve these things, right? Here we think of it as conjugation. So the covariant derivative of the pullback is the conjugate of the covariant derivative. Okay, so that's three different ways to think about connection, and yeah. So let's. Okay, that doesn't work. Let's think about. So when you think about what stabilizer of a connection is, I'll say it. So using Peter's definition, we can see that another way of, so connections are an affine space. So I should be able to write this connection as a affine difference from the original connection, and I can do that, and the difference is this guy. Okay, this needs a little bit of interpretation. What's the covariant derivative of this automorphism? Well, in the case in the case where my Lie group, like in the case of UN, has a faithful representation, then I think of U as a section of the endomorphism bundle where it has a connection already. And then I take its covariant derivative in that sense. Yes?
Please invite the questions.
Yeah, sure, go. Yeah.
So this permits to associate with a curve in the tangent space, a curve with the manifold. And is there such a relation if I take a curve?
We have a curve, sorry, a curve in the manifold lifts to a curve in the total space of the bundle.
Yeah.
Right?
Does this extend to curves which are as irregular as Brownian motion? For example?
Does it extend? We'll have to discuss that after. Well, but Brownian curves are continuous, right? Yeah. So, they don't have. Okay, that's a good question. A for the question. F for I don't know. But that's a really interesting question. Oh dear. That was a very dangerous question because I might think about that question instead of the rest of the lecture. It's okay. Well, focus. I got it. Okay, good. That's the thing. But you notice then that U star A equals A implies that, well, that's 0, which is if and only if that's 0. So U is a parallel section. And in particular, U is determined by its value at any x naught in x, any base point. So right. So let's look at an example. Well, if I take something, a z in the center of the group, right, then this element gives me an automorphism of P, right? Because it's central, and the automorphism sends P to P times Z. Right? This isn't usually an automorphism. The multiplication by elements of G aren't usually automorphisms of the bundle. They don't commute, but if it's in the center, it does. And in particular, so e.g., if Z is e to the I theta times the identity UN, then of course this guy, on the other hand, preserves every connection, right? Because this is a gauge transformation, which is right multiplication by something in the group, and by definition, connections are preserved by that property. Okay, so that's there are all these little pieces of poop that I need to tell you before we can really get going, because it's just like this thing. So the thing that really acts in an interesting way, the kind of real gauge group, is GP mod the center of G. Okay, but now right, so we want to understand what so to understand better stabilizers, we should think about the holonomy representation. So again, if I have here's my principal bundle sitting over X, and then I pick a base point. If I have a loop in the base, and a connection, then I can take the holonomy around the loop, and the holonomy of the connection around gamma is then it's an automorphism of the fiber of the bundle at X naught. And so this is what, when I parallel transport around this curve, if I pick this point, then this point is related to this point by the action of this automorphism. Right. Holonomy and maybe at X naught. Now, you can check that the holonomy. So the holonomy, by the way, doesn't depend on a parametrization. And if I concatenate loops, then the holonomy is multiplicative. So there's a so the holonomy of A is a kind of representation of the space of paths based, space of loops based at X naught to the automorphisms of P automorphisms of the fiber of P, right? And it's a, that's a representation in the sense that this is, we're not taking homotopy classes, but this loop space is still a monoid, and it's a representation of that monoid. And in fact, it's A is determined by this holonomy representation up to gauge transformations to use in here, so that U at x naught is the identity. We're not going to use that yet, but that's an important point. Yes?
Why is it not a representation of pi?
Because it's, so there's an interesting question. When is it actually a representation of the fundamental group, right? And then we want the holonomy not to notice the homotopy class of the path. That happens exactly when the connection is flat. So that's an excellent point to make. Note A is flat. In other words, FA equals 0 if and only if the holonomy representation descends to pi 1. Okay. Okay. Good. Good. Yeah. All right, so so now this automorphism group is a copy of G. We just not identified canonically with G. But this is isomorphic to G, right? What's the stabilizer of A? So the kind of, well, let's make it a proposition. So remember, the stabilizer of A, we can evaluate at x naught, and that gives us something, let's call it the stabilizer at x naught of A. That's a subgroup of the automorphism group of the fiber, which is identified with G, but not canonically. And this is an isomorphism, and this image is the centralizer, the stuff that commutes with the image of the holonomy representation. Okay, so so that's kind of an exercise, but it tells you it tells you what the possible stabilizers are. They are the groups that are centralizers of some subgroup, right? So for, say, G equals UN, then, well, again, we can take our associated vector bundle. It's going to have a kind of splitting into a whole bunch of pieces by A. I'll have an A invariant splitting, and I'm going to say it. So, on some of these, it'll be the diagonal scalar multiplication, and on some of these, and then there'll be big factor where essentially the representation's trivial and it's some unitary group. So, if and there might be several summands like this. So, the simplest situation, if the representation has big enough image, then the stabilizer is U1. If its image is in U1, then its stabilizer is UN. Right? So if the image of if the representation has, if it's irreducible, if it's an irreducible representation, then, which may, by the way, it now makes sense to talk about an irreducible representation, a connection being irreducible if its holonomic representation is irreducible. So if the representation is irreducible, its stabilizer is U1. If it's mapping into U1, but it's on an n-dimensional vector space, its stabilizer is UN, and then you can have a decomposition where it's bits of one type and bits of the other type. If you have something like something simple like SO3, the things that can be, the possible thing, the subgroups that can be stabilizers are these four, these six subgroups. It's clear what this one is. That's this guy. This is, well, this one is the plus or minus ones, but the determinant equals 1. That's this SO2. The O2 is the things of the form a 2x2 matrix and its determinant, and that's something that has kind of, SO3. And you notice in this picture, as with all these pictures, if I take the centralizer, it flips. So there's an involution on these guys by taking centralizers. This is its own centralizer. This is its own centralizer. The centralizer of this O2, well, the centralizer of this O2 is that Z2. And the centralizer of this Z2 is that O2. The centralizer of the trivial group is the whole group. The centralizer of the whole group is the identity. Right? That's something that happens in general.
Sorry, Tom, I got lost. What are you doing here? What are these?
So this is the list of, well, possible stabilizers of an SO3 connection. I'm not saying that they're realized, but I'm saying that from what we know, that's what could possibly happen. Right? So they're the subgroups that are the centralizer of some other subgroup. The other subgroup may be more interesting, right? But so the image of the holonomic representation, who knows, some interesting subgroup, but its stabilizer has to be one of these guys, right? And that's the thing that we really care about. We're trying to understand the quotient of connections by the gauge group, and we need to know what the possible stabilizers are. Right? And you notice, if it was SU2, it'd be much simpler. Sorry. For SU2, the choices can either be Z2, plus or minus 1 subgroup U1 or SU2. Right. Okay, so great. So now, what do I want to say? Okay, stabilizer is good. Yep.
Do you say anything about torsion-free super connection? Torsion-free?
I mean, they're connections in a principal bundle, so there's no torsion. I mean, you know, yeah. I mean, okay. Right. Okay. So now we want to kind of deal more seriously with doing this quotient business. So we're going to look at a cycle of completions of connections, you know, of A and G. I just want to answer your question now. So, I mean, if I have a, you know, if I want to talk about, you know, non-smooth connections but I have a smooth vector bundle. If I have a smooth vector bundle, then what I need to do, I need to be able to define that horizontal splitting in a non-smooth situation. But it's a subbundle of a bundle that's smooth, and the splitting is determined by a section of a bundle of endomorphisms. Now, a bundle of endomorphisms is a linear thing, so I can talk about LP sections of that. Okay? Yeah, sure. But I don't know about lifting Brownian paths. Okay, so what we're going to do, so Sobolev spaces. But I know since many of you do pseudo-holomorphic curves, you know all about Sobolev spaces, right? Sure you do. Anyway, so what we want to do is look at, we're going to define, so if we, I don't want to spend too much time on this, but we're going to define, we have a covariant derivative. So if we have a vector bundle on X, Cn or Rn or whatever, with a connection, and inner product, so it's a metric connection in an inner product, then we can talk about Sobolev spaces of sections. We can define LPK sections of this guy to be the completion, of smooth sections with respect to the LPK norm, which depends on picking a connection, and it's the integral over x of the kth covariant derivative of v to the p plus nuts. So that, so k is a natural number, p is between 1 and infinity, etc. Right. Now, we're mostly going to worry about the case where p is 2. Sometimes other cases will come up. But the thing that we want to do, so we're going to define the kind of LPK connections in P by taking a smooth connection and so a C infinity connection and look at LPK sections of X of the bundle of one forms with values in add P. And then we want to, there's gauge group, LPK gauge group, when can we define that? That's a little more interesting, but if we think of the situation where, say, in the unitary groups situation, what we're going to do is look at U, which are LPK sections of the bundle of endomorphisms of E, which are unitary, but or we only ask this equation to hold almost everywhere. Okay? So these are sections of a vector bundle, so it makes sense to talk about LPK sections. The complication is that we would like them to be unitary. And the sense in which we're going to ask them to be unitary is in this almost everywhere sense. If P and K are such that this consists of continuous things, then that's not important. But if you ask me about Brownian things, then I don't know. But we'll...
It's been a long time. You don't want them to keep outside.
Yeah, okay, good. But now, remember the action of U on A is by this formula, right? And we want to know, when does this make sense? So, and the answer is that, let's see. So, so let's say it this way. Okay. You know, so if this guy's an LPK gadget, we'd like this to define an LPK gadget as well. And in order to do that, we probably need U to have one more derivative than A. Right? So the natural guess, and then we need to see when it'll work. Is the LPK plus 1 gauge transformations. Now that's we'll see that that's often true, but not always true. By the way, yeah. Another, I mean, even better question to ask than which U's preserve this guy is, suppose, you know, suppose that UA and A are in LPK. What does that imply about U? Okay, so yeah, that's what we so the thing that we'd like to see is that you know, the kind of best answer to thinking about this question is that if we have a connection so that its gauge connection so that it and its gauge transform are in LPK, then we'd like to see that the gauge transformation is actually an LPK plus 1. Right, so it's really the full symmetries of that guy. And then we could even look at U's where we, assuming it's just, say, an LP, still makes sense to ask this. But then we could, try and prove that U has more regularity if we know it does something nice to a particular connection. Okay? Now, okay. The basic tool of the trade in this story is the Sobolev embedding theorems. So, so in dimension n, for X is an n manifold, assuming it's compact, then LPK sections of this guy embed into LQL sections if the conformal weights allow K minus N over P is bigger than L minus N over Q. Yeah, and you can't get something for nothing. K has to be bigger than L, and we want these guys to be, it's interesting in the situation where these guys are negative, that these guys don't consist of continuous things. Once they consist of continuous things, the story becomes easier. On the other hand, LPK embeds into Holder space if, again, K minus N over P is bigger than, oh, sorry, yeah, equality. Bigger than L plus alpha. Alpha has to be positive, and still K has to be bigger than L. Okay, so in particular, we're mostly interested in 4 manifolds, so that the things that we'll use all the time are that L21 embeds into L4, L22 embeds into LP for all p less than infinity, and L23, etc. That's contained in the continuous guys. Okay? So those are the important versions that we want. Let's notice that there's already something interesting to be noted about the curvature in dimension 4. So if A is an L21 connection in P, then its curvature, which is this guy, well, if A is an L21, that's an element of L2. This, by the embedding, this is in L4, this is in L4, so the product is in L2. So this is in L2. So L21 is the kind of interesting, interesting dimension. That's when curvature is at L2, and we're trying to, the basic thing we know from the first lecture is that for instantons, the L2 norm of the curvature is a topological invariant. It's the absolute value of the Pontryagin number. Okay. Okay, and so the space of connections is an affine space, so it's a Banach manifold or Hilbert manifold if P is 2. What about the gauge group? When is it a Lie group in the sense of infinite dimensional manifolds? Well, the claim is that proposition, if we're in the continuous range, let's say K plus 1, then GLPK plus 1 of P is a Banach-Lie group. And the, the sketch of the proof is to use the usual proof. So we're going to sketch the proof when G is UN, and we're going to generalize the proof in finite dimensions that tells you that UN is a manifold. What we're going to do is look at the map. So you notice this guy is contained in continuous things, and once you have containment in the continuous things, then what you want to show is that in general, let's say this. Suppose we have V is not just a vector bundle, but a bundle of algebras. E.g., V is endomorphisms of some other vector bundle. If LPK of V is contained in continuous sections of V because of the embedding theorem, then the space of sections is an algebra under pointwise multiplication. That's an exercise. But once we know that, then X was compact. Still compact. That's good. So what we want to do is for this unitary group, we're going to look at so let's let V be an LPK plus 1 section of the endomorphisms of, let's call it phi, okay? And we're assuming that we're in the continuous range. So we can map this guy to this, which is still in LPK plus 1 of NV, but now it's a symmetric endomorphism, right? And the claim is, the next exercise show that this is a smooth map of Banach manifolds and the identity in LPK symmetric endomorphisms is a regular value. Well, we want to imply the implicit function theorem or inverse function theorem in infinite dimensions, and in order to apply that in the Banach space case, we need to have a split kernel. In the Hilbert space case, you don't need that extra hypothesis, so that's an exercise. But the proof of this is the same, on the algebraic level, it's the same proof as it is in finite dimensions. This is an algebra map. Algebra maps are, multiplication is just smooth in a topological algebra. I mean, it's supposed to, you know. It means that the kernel admits a closed complement. So we want the implicit function theorem for smooth maps of Banach manifolds. So yeah, DF having a right inverse, continuous right inverse. Yeah, that's right. So normally you just care that the differential is surjective, but you need, in general, to know that there's the kernel of the differential at your point, and you need to know it's supposed to map onto the tangent bundle at some point. Yeah. This is supposed to be surjective, and like you say, you would like to have a splitting, or it has to be a closed subspace that's complementary to the kernel. Okay, but like I said, if you play around with the proof in finite dimensions, you'll easily construct a closed complement. The closed complement, this is already surjective on the symmetric endomorphisms. The closed complement is the skew symmetric endomorphisms. And so it's not hard to prove this. And then you know that the preimage, so if I call this map F, then F inverse of the identity is the gauge group, is a smooth manifold. Smooth manifold. Not only is it a smooth manifold, but because then multiplication in the gauge group is just restriction of the multiplication in the algebra. So it's also a smooth map. And so this is an infinite dimensional Lie group, which is now, I appreciate that not everybody has the implicit, just differential topology of infinite dimensional manifolds in their back pocket. But in fact, right, real analysis, Rn, what's Rn? Start off with a Banach space. Yeah, anyway, oh well. But now now we can say, so, next proposition is that if k minus this is positive, then the LPK plus 1 gauge transformations act on LPK connections is a smooth map. So again, from the formula that was just here, U star of A is A plus U. Right. The thing that you see is that this. It's sort of an easy exercise to see that differentiation maps is a smooth map from LPK plus 1 to LPK. So this guy is going to be smooth. I mean, the map that sends U to this guy is going to be smooth. And then we're in a situation where this guy, the multiplication of this guy on this guy is smooth. So it's a smooth map. And then the things that we want to show now are that this quotient space. So I'm going to, let's, in this context, this quotient space, the first thing we want to see is that this is Hausdorff. And then we want to see that it satisfies the fundamental theorem of transformation groups holds in this context, namely that, so the fundamental theorem of transformation groups tells you that if you have a smooth group, a Lie group acting smooth, compact Lie group acting on a smooth manifold, this is definitely not a compact Lie group, but nonetheless the theorem holds, then, so G is acting on this X. I can look at the orbit Gx, take a transversal to the orbit, and then a neighborhood of the orbit you can identify with the orbit times a transversal divided by G. I'll explain that a little bit more carefully next time. But two things that happen in the finite dimensional case happen in this non-locally compact case because we're looking at because the group is a compact Lie group. These are both false if G is not a compact Lie group. In general, we'll see that too. So that's it. Questions? Aishrath, question? No. It's all obvious. Ali, question? No. Josh? No. Oh, well.
No class next week, right?
No class next week, that's right.
What are you planning to do next lecture?
Next lecture, well,